Hello my friends and welcome back to the You Can Do TV channel. Today we visit Bronneberg's factory to see how a metal baler is built, one of the toughest machines in the recycling world. Bronneberg is a well-known player in the global recycling market, offering complete solutions for processing scrap metal, cars, cables, and even cardboard. The process begins with the backbone of the machine, the frame. Thick steel sections are positioned and squared, then welded into a rigid structure that can survive repeated compression cycles. Welding here isn't just joining metal. It's creating a load path. The baler's body must take enormous pushing forces without twisting, so welds are laid with careful sequencing to control heat and minimize distortion. Now the frame moves to milling. Even a powerful machine needs precision, especially where sliding parts meet and where cylinders mount. Large milling equipment trues up reference surfaces, cuts mounting faces flat, and ensures hole locations line up exactly across the structure. This is the difference between a baler that feels smooth and controlled and one that wears itself out early. With the frame complete, technicians begin assembling the structural modules, the press box, guides, lid components, and reinforcement plates. For models like the Bronneberg Super 2 hinge lid scrap baler, the press box is engineered around cutting and pre-compression. All-round cutting knives on the hinged cover help bite into bulky scrap, while rotating knives on three sides of the press box help shear and condition material. The hinged lid works almost like scrap shears, so pre-treatment is often unnecessary, saving time, handling, and energy on the yard. Next comes the hydraulic heart of the machine. Cylinders, pumps, manifolds, valves, and hoses are installed and routed with a focus on both performance and serviceability. Hydraulics translate motor power into controlled motion. Massive forces applied smoothly, then held steady under load. Lines are clamped, protected, and labeled. Fittings are torqued and checked, because in high-pressure systems, small mistakes become big leaks. Step by step, the baler starts to look alive, like a skeleton gaining muscle and nerves. Final assembly brings everything together: guards, sensors, electrical wiring, and controls. Bronneberg designs for usability too. Simple operation with remote control and automatic function means the operator can stay at a safe distance while the machine cycles through its sequence. Options like a pre-loading box can make loading easier, and the baler's low overall height helps integrate it into real scrapyard workflows. Then comes the moment of truth. Testing and trial runs. The machine is filled with hydraulic fluid, bled, and pressurized. Every cylinder stroke is checked for smooth travel, every valve for correct response, every safety system for reliable shutdown. Under controlled conditions, the baler runs through repeated cycles: compress, cut, hold, release, while technicians monitor pressure behavior, alignment, noise, and heat. Only after it proves it can deliver consistent force and clean motion does it earn the right to leave the factory. and the mission behind it matters. Recycling ferrous scrap metal is far cheaper than mining virgin ore, and it brings major environmental advantages, about 75% energy savings, 90% savings in raw materials used, 86% reduction in air pollution, 40% reduction in water use, and 76% reduction in water pollution. A metal baler isn't just a machine. It's a tool that helps turn yesterday's scrap into tomorrow's steel, again and again. This scrap baler works by converting loose aluminum or stainless steel scrap into a dense, transport-ready bale using controlled hydraulic force. A 40 horsepower motor drives a hydraulic pump that pressurizes oil and feeds it to the main cylinder. That hydraulic pressure pushes a 10-inch main piston forward inside the compression chamber, sweeping scrap inward and forcing out trapped air and voids. As resistance rises, the system builds to its rated 90-ton pressing force, compacting the load into a tight block with consistent density. Valves regulate speed and pressure through each stage: fast approach, high force compaction, and pressure hold, so the machine can pack scrap without shock loads. Once the target compression is reached, the hydraulics reverse, the piston retracts, and an ejector sequence pushes the finished bale out of the chamber for tying and handling. This unit was also used for full warranty testing, meaning it ran complete press and eject cycles under load to confirm force output, hydraulic stability, motor performance, and repeatable bale quality. Copper scrap baling is all about turning loose, springy material into a dense, stackable block that's easy to store, ship, and sell. In the McIntyre 25B demo, copper tube, copper wire, and bulky items like hot water tanks are fed into a strong steel compression chamber. The baler's hydraulics do the heavy work. A main ram drives forward and squeezes the load against the chamber walls, forcing air gaps out and locking the copper into a tight mass. What makes the 25B practical for real scrapyards is how it deals with awkward, oversized pieces. Cutting blades on three sides of the box shear protruding tube or wire as the ram advances, trimming the load so it fits cleanly inside the chamber instead of jamming. That means you can load faster and waste less time pre-cutting material. As compression continues, the ram cycles, press, retract, and press again until the bale reaches a target density. Once compacted, the baler opens the discharge side and the ram pushes the finished bale out, ready for strapping or stacking. A fast cycle time keeps throughput high, and the simple, heavy-duty build is designed for long service life. Exactly what a recycling facility needs when copper volumes fluctuate and every minute of uptime matters.
Hyundai HX180 excavator fitted with the Powerhand VRS attachment tackles the task of dismantling vehicles efficiently. To separate valuable materials, the operators align the machine so the VRS attachment can grasp and manipulate components securely. Simple mechanics, but serious strength at work. As the arm maneuvers, the VRS attachment compresses sections of the vehicle, breaking down unwanted structures while leaving recoverable metals and plastics intact. Each movement is calculated, focusing on extracting materials that maximize resale or recycling value. Feels like this machine doesn't waste a second thinking. Shocks, panels, and engine parts are systematically removed, sorted, and stacked for the next stage. Once the mainframe is stabilized, the VRS attachment tears apart smaller internal structures. Seats, dashboards, and other internal fittings are carefully disassembled. Operators and the excavator collaborate seamlessly to ensure no components are lost or damaged beyond utility. The torque doing the talking here. Even the tiniest fittings are treated like they matter. The process is repeated for every vehicle, creating a workflow that balances speed and material recovery. Finally, the separated materials, steel, aluminum, plastics, and copper, are organized for further processing or resale. Each segment of the vehicle is treated to optimize profit while minimizing waste. Somehow, the workflow feels oddly calm despite all the power at play. Throughout the VRS process, efficiency and safety remain priorities. Operators monitor attachment angles, hydraulic pressure, and vehicle stability to prevent accidents. The Powerhand VRS attachment's design allows it to handle a wide variety of vehicle types, demonstrating versatility in recycling operations. Somehow the whole process looks almost too easy for what it's doing. Every car dismantled seems to tell a story of recovered value. Every vehicle dismantled contributes to a sustainable recycling effort, ensuring that each component finds a second life.
A rubber mixing mill is a key machine used in the rubber processing industry to create uniform rubber compounds. The following outlines the working process of a rubber mixing mill. The process begins by loading the mixed rubber compound from an internal mixer or a Banbury mixer. If an automated rubber material feeder mechanism is unavailable, the material is fed manually from the front side of the mill. The rubber is fed between the front and rear rolls of the mill, where it rotates continuously to form a homogeneous sheet. Initially, the operator picks up rubber lumps that fall into the mill pan and refeeds them between the rollers to ensure consistent mixing. Maintaining the correct quantity of rubber compound is crucial. Any material loss during the mixing process can result in an incorrect ratio of curing agents, leading to compound rejection. The operator adjusts the nip gap at various stages to achieve a properly mixed and well-dispersed rubber compound. If the compound rolls onto the rear roll, the operator manually transfers it back to the front roll. This repositioning ensures optimal mixing efficiency. Once the rubber sheet reaches a uniform consistency, additional ingredients such as sulfur and other curing agents are added. These ingredients are pre-measured to ensure accurate formulation. The compound is repeatedly passed through the rollers to disperse the chemicals uniformly. The rubber sheets are cut, rolled, and refed between the roller gaps for thorough mixing. Any loose material in the mill pan is also refed to avoid waste and maintain uniformity. Operators must wear protective gloves to safeguard against sharp tools and harmful chemicals. Maintaining a safe distance from the rollers and the belly bar is essential. In case of accidental pressing, the belly bar stops the machine immediately. After the mixing process, the rubber sheets are cut into specified sizes, labeled, and dipped in an anti-tack chemical solution to prevent sticking. The sheets are then air-dried and marked with identification and production batch details. Once approved for quality, the finished rubber compound is moved to the designated storage area. The operator must create a production report documenting the target quantity, actual production output, and any delays with reasons for reference and continuous process improvement. The process of making a green tire refers to the initial stage of tire production, where uncured rubber components are assembled into a complete tire structure before vulcanization. The term, green, denotes that the tire is unvulcanized and soft, ready for molding and curing.
Oh, so that's cut already? Yeah. I was wondering how to do that. I was like, wow, she's strong. Rapid fire rubber.
The process starts with blending raw rubber with reinforcing fillers like carbon black, silica, and various chemicals to enhance performance characteristics. This compound is mixed in giant mixers called Banbury mixers or kneaders. The mixed rubber is shaped into various tire components such as the inner liner, for air retention, body plies, for structure, beads, for wheel attachment, belts, for strength, sidewalls, for protection, and tread, for road grip. Each component is precision processed through calendaring, extrusion, and cutting. The green tire is assembled on a tire building machine. Layers of rubber components are sequentially applied to form the tire's basic structure. The inner liner is placed first, followed by body plies, beads, belts, and the tread. Each layer is precisely aligned and stitched using rollers. After assembly, the green tire undergoes a quality check for dimensional accuracy and uniformity. It is then transferred to the curing or vulcanization stage, where heat and pressure transform it into a durable, elastic product.
This one doesn't because it's so wide.
The green tire making process is critical, as precise assembly ensures the tire's performance, safety, and longevity in its final vulcanized state. The Ringbuilder 3000, RB3000, designed by Marangoni Retreading Systems, is a high-efficiency tire retreading machine built for large retreaders. It can produce at least 200 ring tread tires in an 8-hour shift while occupying minimal floor space and ensuring maximum automation. Its advanced design allows for significant productivity, reduced labor costs, and faster processing times, making it ideal for large-scale tire retreading operations. The RB3000 combines two essential phases of the cold retreading process, applying the cushion gum and the ring tread. It uses two spindles positioned 180 degrees opposite each other, enabling simultaneous operations on two tires. While one spindle extrudes the cushion gum directly onto the casing and fills any craters, the other applies and rolls the ring tread. This integrated process eliminates manual steps such as tread measuring, cutting, and splicing, which are typically required in conventional retreading methods. The fully automated cycle ensures that every tire is uniformly processed, reducing material waste and enhancing efficiency. The machine's precision ensures consistent under-tread thickness and eliminates oxidation-related waste from tread ends. The result is a perfectly retreaded tire that's ready for curing, produced in significantly less time compared to traditional methods. Automation also optimizes the working space by removing the need for cutting stands and tread lifting hoists. This streamlined setup reduces idle time, increases operational efficiency, and minimizes the required workforce. Each tire retreaded with the RB3000 saves approximately 5 minutes compared to traditional methods, 3 minutes from faster building time and 2 minutes from eliminating tread handling and waste management steps. The ring tread technology used by the RB3000 is spliceless, ensuring a seamless retreading surface for superior tire performance. This process contributes to Marangoni's growing market share, with more than 25% of Europe's cold retreaded tires produced using this technology. Dunlop has been producing aircraft tires in the UK for over a century, with its factory in Birmingham known for exceptional engineering. The tires endure extreme conditions, combining the load-bearing capacity of off-road tires with the high speeds of Formula One racing. Dunlop's global expansion includes a new facility in North Carolina, providing tire distribution and retreading services across the Americas. Each tire undergoes rigorous FAA certification, ensuring safety, reliability, and high performance, reflecting Dunlop's commitment to quality in every product. The remold tire production process is a highly technical operation focused on recycling used tire casings into high-performance tires while ensuring maximum safety and environmental sustainability. Upon arrival, used tire casings undergo rigorous inspections. Advanced inspection machines use chirography in a vacuum with interferometric laser systems. This technology highlights internal separations or defects with exceptional accuracy. If any casing fails, it is rejected or downgraded for non-road agricultural use. Approved casings are inflated incrementally from 2 to 9 bars in a pressure tester. This process checks for any signs of weakness or failure under pressure. The casing's old tread and sidewall rubber are removed using high-speed revolving rasps and brushes. This computer-controlled process ensures precise dimensions, creating a perfectly prepared surface for the new tread application. Technicians inspect the buffed casings for any remaining imperfections. Defects are removed, and damaged areas are repaired using industry-standard hot cure patches. These patches, reinforced with inner belt layers, often surpass the strength of the original casing. The casing is sprayed with adhesive cement, creating a strong bonding surface. Any surface irregularities are filled with extruded gum, ensuring an even and durable base for the new tread. The new tread is applied using a patented computer-controlled process. A continuous strip of premium rubber is wrapped around the casing with precise tension. The bilk tire is placed in a hot segmented mold within a curing press. It is heated to 150 degrees Celsius and inflated to 200 psi using an internal bladder. The heat, pressure, and curing time vulcanize the rubber, forming the required tread pattern and depth. Tire cutting machine is designed to cut tires into smaller pieces for recycling or disposal purposes. The most common types include the tire shredder, tire cutter, and tire sidewall cutter. The tire shredder is designed for breaking large tires into smaller, manageable pieces. These machines are typically capable of processing up to 15 tons of tires per hour, depending on their motor power and blade configuration. The shredder uses rotating blades to cut tires into pieces that range in size from 2 inches to 6 inches, making them easier to transport and further process. A tire cutter is used to cut tires into specific shapes or sizes, often for more precise applications. Tire cutters can typically cut 10 to 12 tires per minute, depending on the tire size and machine specifications. These machines feature hydraulic-powered blades that can easily slice through the steel-belted structure of the tire. The tire cutter is commonly employed when a specific size or shape of tire sections is required for further processing in the recycling plant. The tire sidewall cutter is specifically designed to remove the sidewalls of tires, which are typically made from tougher material than the rest of the tire. The sidewall cutter uses high-force hydraulic blades to separate the sidewalls from the rest of the tire. This machine can process about 8 to 10 tires per minute, depending on tire size and the machine's efficiency. The sidewalls are often separated for different types of recycling, as they may be used in creating products like rubber mats or other industrial items. Tire cutting machines come with various key specifications that vary based on the type and capacity of the machine. Motor power typically ranges from 30 kilowatts to 250 kilowatts for most models. High-capacity tire cutting machines can process up to 40 to 50 tons of tires per day, depending on the workload and tire size. These machines are also capable of handling tires ranging from 14 inches to 48 inches in diameter. Some machines are equipped with single blades, while others have multi-blade configurations that allow for higher throughput and efficiency, enabling them to process multiple tires simultaneously. Tire cutting is a significant process in Karachi, Pakistan, where scrap tires are recycled to extract rubber for various industrial applications. This process involves cutting worn-out tires into manageable pieces to separate rubber, steel wires, and fabric. The first step is removing the steel bead from the tire's edges using a bead cutter. Then, a tire cutting machine slices the tire into smaller strips or chunks. Depending on the desired output, the rubber can be further processed through shredding machines. The extracted rubber is commonly used in producing playground surfaces, rubber mats, and reclaimed rubber products. Karachi's tire recycling industry thrives due to the availability of cheap scrap tires from automotive workshops and scrapyards. However, the industry faces challenges such as limited access to advanced machinery and environmental concerns related to improper waste disposal. Efforts to modernize recycling methods and ensure eco-friendly operations can improve sustainability while creating economic opportunities for local communities in Karachi. The process of making durable tire sandals involves several key steps. Sole preparation. The sole is cut from old tires using a sharp cutting tool. This provides a tough, wear-resistant base. Groove marking. Grooves are marked on the sole's surface to enhance traction and prevent slipping. Strap cutting. Straps are cut from tire sidewalls or other sturdy materials. Their width and length are measured precisely for comfort and fit. Punching and inserting. Holes are punched in the sole for strap attachment. The straps are then inserted and secured with knobs or plugs to hold them firmly in place. This traditional method creates long-lasting. In Germany, there's about 2.5 million tons of packaging waste every year, much of which ends up in the yellow bag or yellow bin. At a sorting plant in southern Hessen, Milo Company aims to increase the proportion of recyclable waste that can be turned into new products. Waste collected from yellow bags and bins in the surrounding region often contains materials that don't belong there, such as non-returnable packaging and various types of household waste. Examples of recyclable plastics include high-density polyethylene, HDPE, bottles, polyethylene terephthalate, PET, containers, and polypropylene, PP, bottle caps. These plastics, however, are mixed with non-recyclable materials. Waste from a 300-kilometer radius, covering Bavaria, Baden-Württemberg, Rhineland-Pfalz, and Hessen, is gathered, amounting to 120,000 tons of waste annually, approximately 5% of Germany's total yellow bag waste. The sorting process is largely automated. In a vast machine hall, a 2.5-kilometer conveyor belt moves the waste through various stages. Initially, the waste passes through a large rotary sieve, where materials are separated by size. Smaller pieces fall through holes, while larger items proceed to additional drums, creating 5 different size streams. The next step involves an air separator that uses wind blasts to remove lighter materials like foil. This helps isolate hard plastics, making further sorting more efficient. An infrared scanner then identifies specific plastic types, enabling air pressure jets to separate PP bottle caps, PET containers, and HDPE bottles from the material flow. Despite the automation, workers manually inspect the sorted material to ensure quality. About 1/3 of the original waste consists of mixed plastics and residuals, including old shoes and wood, which are designated for incineration. The remaining plastics undergo over 30 sorting procedures, resulting in HDPE, PP, and PET bales with a purity level of 94 to 98%. These bales are valuable secondary raw materials supplied to companies in Germany and neighboring countries. Sorted HDPE bottles are repurposed into pipes or specialized pallets. PP caps become flower pots or buckets, while PET containers are turned into fibers for clothing or outdoor furniture. However, these products have a limited lifespan and eventually end up in waste incineration plants. Creating a full-fledged recycling cycle requires further processing. In Thuringia, Cystic Plastics operates a specialized plant in Eisfeld dedicated to this task. HDPE bottles are shredded, cleaned of residues like shampoo or yogurt, and sorted again. This process yields a colorful mixture of HDPE flakes. A color sorting system ensures purity. HDPE particles are fed one by one over slides while sensors detect and separate unwanted colors using compressed air. This system operates at high speed, processing tens of thousands of flakes per minute. The resulting HDPE flakes have a purity level of over 99%. The flakes are melted at 220 degrees Celsius in an extruder, filtered, and purified again. The molten plastic is cooled and processed into granules, forming a high-quality raw material used throughout the plastics industry. Similar processes apply to PP caps, ensuring their reuse. Production of recycled products. Each year, the Eisfeld plant processes around 20,000 tons of material from yellow bags. While only a portion of the waste currently receives full treatment, production capacity is expected to grow. "We can already turn plastic from yellow bags back into usable plastic," says a company representative. "We aim to expand into food-related products, starting with cosmetics and eventually moving into the food industry. This will take several years, but our goal is to produce hygienic, high-quality plastic." Recycled materials from Eisfeld are in high demand, especially among cleaning product manufacturers like Werner and Merz in Mainz. The company produces over 130,000 tons of detergents annually and uses HDPE granulate from Eisfeld to manufacture its bottles. The recycled granulate is melted in a special extruder and molded into bottles using air pressure. Excess material is trimmed, and the finished bottles are filled and delivered to stores. Werner and Merz produces around 5.5 million bottles annually using 100% recycled plastic from yellow bags. PP caps are also made entirely from recycled material. "We use recycled plastic from yellow bags for our PET, HDPE bottles, and PP caps," the company representative states. "We aim to increase this percentage while seeking market partners to reduce recycling material costs." Despite technological advancements, PET granulate from yellow bags remains insufficient in quantity. To meet production needs, the company blends it with PET granulate from deposit return systems. This hybrid material is used to create more than 80 million bottles each year. Toward a circular economy. The ultimate goal is a closed-loop recycling system where an HDPE bottle becomes another HDPE bottle, a PP cap becomes another PP cap, and a PET bottle becomes another PET bottle. This approach conserves raw materials and energy invested in plastic production. While only a fraction of packaging waste from yellow bags currently gets recycled, experience shows that such waste can indeed support a material cycle. Every successfully recycled bottle counts toward reducing environmental impact and conserving resources for future generations. The 1000 liters triple-layer water tank automatic blow molding machine is a highly efficient, fully automatic system designed for producing large water storage tanks, including loft tanks. The machine uses advanced blow molding technology to create water tanks with exceptional strength and durability, making it ideal for applications that require reliable water storage. Key features of the machine include PLC control with man-machine interface, which provides precise control over the entire process, allowing operators to monitor and adjust settings easily. The FIFO, first in, first out, accumulator head ensures uniform extrusion, allowing for consistent production. The AC variable frequency drive on the extruder controls the speed of the extruder motor, ensuring energy efficiency and smooth operation. Hydraulics are powered by Yukon Hydraulics, known for their reliability and precision. This ensures smooth operation of the blow molding process, which involves inflating a heated plastic piston inside a mold to form the shape of the water tank. The machine is designed for continuous operation, with a focus on high performance and durability, making it a true workhorse capable of running 24/7 with minimal downtime. The machine offers several advantages, such as lightweight construction, reducing the need for excessive manpower during operation, and threaded lids, which make it easier to seal and secure the tanks after molding. Optional features include piston control systems for more precise control of the piston thickness and servo-hydraulic systems, which improve energy efficiency and reduce hydraulic consumption. With its combination of advanced features and high throughput capacity, this machine is perfect for manufacturers looking to produce large volume, high-quality water storage tanks with minimal labor and operational costs. The pyrolysis unit, mini reactor, is an advanced tire recycling technology designed to transform waste into valuable products through a multi-stage process. This efficient system converts tires and other raw materials into carbon residue, steel cord, and pyrolysis liquids, offering a profitable solution for waste management. The reactor's end cover opens for raw material loading, which can be done in several ways: tires and bulky raw materials. Two loading windows accommodate various tire sizes. The first window, 1,500 by 470 mm, handles medium-sized tires and larger items through deformation. The second window, 900 by 900 mm, is suitable for passenger and truck tires with a maximum diameter of 1,300 mm. A press pusher efficiently loads tires, supported by interchangeable nozzles for diverse materials. Liquid raw materials are introduced through a reactor fitting, with an optional continuous fluid supply system. The reactor heats for 1.5 hours using an oil burner. If multiple reactors are operating, excess gases from one reactor can heat another. The active pyrolysis phase begins, producing a gas-vapor mixture fed to the condensation line. Pyrolysis liquid separates, while non-condensed pyrogas fuels the burner, sustaining self-heating. Temperature and pressure are controlled through burner adjustments and excess gas flaring. The pyrolysis cycle lasts 6 to 8 hours. After pyrolysis, the reactor cools for 3 hours using an automated control panel. For liquid or metal-free raw materials, full cooling may not be necessary. An outlet tube attaches to the reactor's rotation axis, and a big bag secures the other end. The reactor rotates in reverse, unloading carbon residue into the bag. This process takes up to 1 hour. If the raw material contains a steel cord, it is extracted through a special end hatch using a traction device. The process is dust-free, with the cord deposited into a nearby indoor receiving tank. This step takes about 30 minutes. The Eco Monster single-shaft shredder is a powerful waste reduction machine designed for shredding tires and other challenging materials. Equipped with advanced shredding technology, it efficiently processes up to 12 metric tons per hour of tires, including semi-OTR, truck, and car tires, producing output sizes ranging from 150 mm, 6 inches, to 50 mm, 2 inches. The machine features 24 cutting blades, consisting of 18 fly knives and 9 bed knives made from tool steel, ensuring precision cutting and durability. The cutting chamber measures 1,956 mm by 900 mm, 77 inches by 35 inches, allowing for large material intake. The knives are easily replaceable, minimizing downtime during maintenance. Powering the shredder is a 187 kilowatts, 250 hydrogen phosphide, custom hydraulic power unit, paired with a Hägglunds hydraulic motor. This combination delivers low RPM, high torque shredding, ensuring consistent performance with reduced operating costs. The Eco Monster is versatile, capable of shredding not only tires but also wood, plastics, MSW, municipal solid waste, and even metals. Michelin retreading process. The process starts with a detailed inspection of the used tire casing to determine if it is suitable for retreading. The worn tire tread is removed using high-speed buffing machines, ensuring a consistent surface. The buffing process typically removes 3 to 5 millimeters of rubber while maintaining the correct profile for the new tread application. Technicians manually skive out damaged rubber sections that the buffing process cannot remove. This precise step prevents future failures. Damaged areas are repaired using vulcanized rubber patches. A specialized cement adhesive is applied before filling with uncured rubber, ensuring a perfect bond. Pre-cured tread strips or raw rubber compounds are prepared based on the specific tire type and intended application. The prepared tread is applied to the buffed casing using advanced tire building machines. The tread must be centered and precisely aligned to ensure uniform performance. Industry standards allow about 80% of truck tires to be retreaded if properly maintained. Buffing. The worn tire tread is removed using high-speed buffing machines, ensuring a consistent surface. The tire is placed in a flexible envelope or curing sleeve to maintain pressure during the curing process, ensuring even tread adhesion. Tire retreading is an essential process in the tire industry, helping to reduce costs, conserve resources, and decrease environmental impact. The global tire retreading market is projected to surpass $11 billion by 2026, driven by increased demand from commercial fleets. The tire undergoes curing in an autoclave at approximately 100 to 110 degrees Celsius, 212 to 230 degrees Fahrenheit, for 3 to 4 hours under high pressure. This vulcanization process bonds the new tread permanently. Every retreaded tire undergoes a comprehensive inspection, including pressure testing and visual checks, ensuring safety and performance. The MTB tire recycling line is an advanced technological process designed to manage and repurpose end-of-life tires into valuable materials such as rubber granulates, textiles, and metals. This recycling line encompasses multiple stages, including shredding, granulation, sorting, and cleaning, ensuring efficient material recovery while contributing to environmental sustainability. The process begins with pre-shredding, where tires from light vehicles, heavy goods vehicles, and even mining machinery are fed into pre-shredder. This equipment efficiently reduces tire size while managing risks associated with ungrindable materials. With a custom-built electric drive assembly capable of delivering 99 tons of force, the pre-shredder offsets potential hazards like explosions caused by metallic inclusions. Oversized materials are separated and safely disposed of, ensuring continuous operation. After pre-shredding, tires proceed to the primary shredding stage using the robust shredders. These machines are designed to handle tough materials, reducing them into smaller, manageable pieces between 10 to 100 millimeters depending on the installed grid size. The high-performance shredders ensure a consistent output, setting the stage for further processing. The shredded tire fragments are then transported to the granulation stage. The granulators, known for their high cutting capacity and durability, reduce the material further to sizes as small as 3 millimeters. This uniform granulation is crucial for subsequent separation processes. These machines are not only efficient but also designed for quick maintenance, minimizing downtime. Separation and sorting. Separation is achieved through various advanced technologies, including densimetric tables. These tables combine a fluidized airbed and an inclined vibrating platform to separate materials based on density. Rubber granulates, textiles, and metals are efficiently separated, ensuring high purity and quality of the recovered materials. Material cleaning systems. To enhance the quality of the output, the recycling line includes specialized cleaning systems. The textile cleaning system maximizes rubber and textile separation, achieving up to 78% clean rubber yield. Similarly, the clean wire system processes steel components, producing clean steel with up to 98% purity based on operational settings. End products and applications. The MTB tire recycling line produces various valuable outputs, including tire-derived fuel, clean steel, textiles, and rubber granulates. These materials are used in industries such as civil engineering, automotive manufacturing, and energy production. Tire-derived fuel serves as a sustainable fuel alternative, while rubber granulates find applications in road paving, sports surfaces, and molded products. The retreading process for off-the-road (OTR) tires begins with a thorough inspection to ensure the casing's integrity. This includes visual checks and advanced chirography scanning to detect internal defects. The old tread is removed through buffing, where precise dimensions are achieved, leaving the required amount of base rubber. The casing is measured and inspected again to ensure it meets strict retread standards, even after enduring harsh operating conditions. Next, damaged areas are repaired using specialized techniques. Marangoni's team selects a custom tread design, compound, and depth based on the tire's intended application and machine specifications. Unlike common assumptions, the retreading process involves building the tire using 3 compound layers, not simply attaching a pre-cured tread. The built tire is cured using the autoclave process, ensuring uniform bonding and durability. The Marangoni Recaflex system provides flexibility to groove the tread into various designs based on customer needs. After curing, the tire undergoes final inspections, including visual checks and chirography, ensuring top quality. CWS tire manipulators are specialized attachments designed for handling large off-road tires used in heavy machinery such as mining trucks, loaders, and graders. When mounted on a wheel loader, they enable safe and efficient tire maintenance, installation, and removal, minimizing downtime and enhancing workplace safety. The system integrates seamlessly with the wheel loader's quick coupling mechanism, allowing for easy installation and detachment. This attachment is controlled through the loader's hydraulic system, giving operators full control from the cabin using joysticks or a control panel. This setup ensures precise and effortless tire handling. The manipulator consists of hydraulic arms equipped with adjustable clamps that securely grip tires of various sizes. These arms are designed for heavy-duty applications and can handle the immense weight of off-road tires. The adjustable nature of the clamps ensures a secure hold, preventing tire slippage during transport or installation. One of the key features of the CWS tire manipulator is its ability to rotate tires 360 degrees and tilt them as needed. This functionality allows for precise alignment of the tire with the vehicle hub, reducing the need for manual adjustments. Additionally, the system supports side shifting, making tire positioning more accurate and efficient. Safety is a top priority in the design of CWS tire manipulators. They come with load-holding valves to maintain tire grip, pressure sensors to monitor clamp force, and emergency stop functions for added security. These features minimize the risk of accidents during tire handling operations. In operation, the wheel loader approaches the tire, and the operator uses the hydraulic controls to open the manipulator's clamps. The tire is securely gripped, lifted, and positioned as required. After installation or removal, the clamps release the tire, completing the task safely and efficiently. Profil Plus specializes in repairing all types of tire punctures using the hot repair method. This process allows tires to be reused, eliminating the need to purchase new ones. It is a cost-effective and environmentally friendly solution that extends tire life while maintaining performance and safety standards. The 3 steps of the hot repair process. The first step in the hot repair process is casing preparation. The damaged tire area is cleaned, buffed, and shaped to create a smooth surface for repair. Any damaged material is removed to ensure proper adhesion of the repair components. This preparation phase is crucial for achieving a long-lasting repair. The next step is repair and vulcanization. A specialized rubber compound is applied to the damaged area, followed by a vulcanizing patch. The tire is then placed in a press or oven, where it is heated to approximately 120 degrees Celsius for about 2 hours. The combination of heat and pressure causes the new rubber to bond securely with the tire's structure, forming a strong and durable repair. The final stage is finishing. After vulcanization, any excess rubber is trimmed, and the surface is smoothed to restore the tire's original shape and appearance. The repaired tire undergoes a thorough inspection to ensure it meets all safety and performance standards before being approved for use. Applications of hot repair. Hot tire repair is commonly used for agricultural and heavy-duty truck tires, place tires, which are frequently exposed to harsh conditions. Agricultural tires can be repaired using either hot or cold methods, depending on the extent of the damage. Heavy-duty truck tires, subjected to high levels of stress, benefit significantly from hot repair due to its strength and durability. An example of this process in action can be seen at Profil Plus affiliate, Literal News Services in Dunkirk, where heavy-duty truck tires are repaired using hot vulcanization. A full repair cycle, from preparation to completion, typically takes about 2 hours. Benefits of hot tire repair. Hot tire repair offers several advantages. It is cost-effective, allowing users to avoid the high expense of purchasing new tires. It is also eco-friendly, helping reduce waste and the environmental impact associated with tire disposal. Additionally, hot repair extends tire life, ensuring that repaired tires can perform as effectively as new ones when properly maintained. The intervention took place in Dunkirk, focusing on the replacement of an OTR, off-the-road, tire using a crane with a grab. This type of operation is often required for heavy-duty equipment in civil engineering, mining, or construction sites where large and rugged tires are used. In this specific case, the crane was equipped with a specialized grab designed to handle the weight and size of the OTR tire. These tires, typically ranging from 24 inches to 63 inches in diameter, can weigh anywhere between 200 kilograms and 5,000 kilograms, depending on their size and construction. The OTR tire involved in this intervention was approximately 49 inches in diameter, weighing around 1,500 kilograms. The operation began with the crane positioned strategically to ensure safe lifting and positioning of the tire. The grab, with a lifting capacity of up to 3,000 kilograms, was used to securely grip the tire, preventing any slippage or damage. Careful maneuvering allowed the tire to be removed from the heavy equipment, which was a large wheel loader, before the new tire was brought into place. The replacement process also involved ensuring that the new tire was aligned correctly and mounted securely. This was done with the help of precise hydraulic systems and the crane's ability to hold the tire steadily during the operation. The entire intervention took approximately 2.5 hours, from initial setup to final inspection, ensuring the OTR tire was correctly replaced and the equipment was ready for operation again. Safety measures were a priority throughout the operation, with the team ensuring that all lifting and handling processes adhered to the necessary safety regulations to protect both personnel and equipment. Laser geometry alignment is a crucial process for ensuring the correct alignment of an agricultural tractor's front axle. This procedure enhances the tractor's performance by reducing tire wear, improving fuel efficiency, and ensuring better handling. The process involves several essential steps that guarantee precise alignment. The first step is inspecting the tractor for any mechanical play or looseness in the components. This check ensures that all parts are secure and capable of providing accurate readings. Next, tire pressures are equalized according to the manufacturer's specifications. Correct tire pressure is vital for obtaining consistent and reliable measurements. Once the initial checks are completed, laser alignment devices are attached securely to the front wheels. Rear rulers are then positioned on the rear wheels, serving as reference points for the alignment process. This setup allows precise front wheel alignment in relation to the rear wheels. To ensure accuracy, a measuring ruler is positioned correctly and set to 0. This zeroing process eliminates any initial measurement errors, providing a clear starting point for the alignment. The actual toe-in or parallelism value is then measured, indicating the degree of misalignment. Adjustments are made by unlocking and rotating the tie rod ends. This process corrects the alignment and provides a direct reading of the corrected value. The final step involves fine-tuning the tie rods until the corrected alignment value matches the required specification, such as -0.20 degrees.